So, welcome. This is our 24-3 lecture. This is our last lecture before exam 2, right? So the next time we're going to be meeting, it's going to be just a review session. I'm thinking like last time, I'll probably just wind up doing a lot of the problems, either homework problems, whiteboard problems, some from the practice set, a combination of kind of everything, just running through a variety. If you've got problems in particular that you'd like to see me do, please go ahead and, join me and let me know. But I think that's the current plan for these things. But we are closing out our chapter on Gauss's law today. Last time we ended up talking about how we can use Gauss's law and calculating flux to find the electric field from what would otherwise be really complicated shapes. And when I say complicated shapes, I really mean spheres and cylinders. Right, on their own, they seem kind of, intuitive, regular, not anything crazy about them, but when you actually have to do the integral to find things like the electric field, that's substantially more difficult. Immediately, you're doing three-dimensional integrals with all sorts of angles, and it just gets really nasty really fast. But Gauss's law was there to kind of save the day. It said, okay, as long as our shape is symmetrical, as long as we can find some sort of Gaussian surface to match the symmetry of that shape, then we can much more easily calculate that electric field by using our definition from flux. Right? And so last time we looked at a sphere, we looked at a cylinder. Today we're going to close that out by looking at our third big shape, right? The infinite plane. So the way that we do this one is, well, we've actually got some more options. Right here in the picture, I've got it drawn in what we call the pill bottle shape, but realistically, I can make anything. Because as we're going to find, it doesn't really matter. I don't specify a radius, I don't specify a length, and I don't really need to. Because if we look at this thing, we remember that the electric field comes perpendicularly out from our surface, right? If I take my definition of Gauss's law, then I can basically say, okay, group this thing up so that it's split right down the middle on top of this plane. On one side, because there's an electric field leaving, I have a positive flux, the left end flux. On the right side, I would have the right end flux. Because my shape has, some uniformity on each end, the area is the same for each of those. It's going to be E times A plus E times A is equal to the charge inside divided by E naught. Charge inside divided by E naught, I have a surface charge density eta. Surface charge density times area gives me my charge. And right there, we recreate our plane of charge electric field equation without needing to go through a really nasty integral. And it's not the nastiest integral in the world, but this was certainly a lot easier than that would be, right? I hope we can all agree on that one. So, just like before though, we keep looking at, let's imagine Gauss's law on the point charge, and then on the sphere. Let's imagine Gauss's law on the infinite line, and then on the cylinder. Let's imagine Gauss's law on the infinite sheet, and now on the slab. So, let's say we have a slab of charge, so a sheet, but with a certain amount of thickness to it, right? It's no longer just two-dimensional, it's got an actual thickness. It's lying in the xy plane, and it's sticking up by plus z naught, it's sticking down by minus z naught, right? So the total thickness, 2z naught. The volume charge density is rho. And it's constant all the way throughout. So first, use Gauss's law to try and find what the electric field would be outside of my slab, and then use Gauss's law in kind of the same way as part A, but now inside. Keep in mind that even though I'm drawing this as a pill bottle shape, I can leave this area of the face as just A, and that's going to make your calculations a lot easier. Call it A in the meantime, deal with it sometime later. Okay, I think I'd like to start taking a look at this one. So, the first thing that we're going to need to do is draw this thing out. So what I'll do here is I'm going to take first a side profile of this thing. So it looks something like this. Here is our z-axis. Here is our not very... Try and see if I can center that up a little bit better. There we go. So this is like my XY plane. Here's my Z-axis. And let's go ahead and color this thing in, right? Let's go ahead and take that step as well. So let's do an even feel. Let's go like a pale blue like that. Yeah, that's perfect. So here is my, as I've called it, side profile. I can also take a top-down view, and it's going to look something like this, right? Where Z is coming out of the page towards us. So, as we've got this thing, we're trying to draw some sort of Gaussian surface like this, more or less, right? And let me see if I can center that up a little bit better. So let's make those lengths almost identical, kind of like that. And one more step I'll do is I'm just going to make sure that we're all clear here that the Gaussian surface, not a physical thing, right? It is an abstract idea to help us solve what the electric field should be. So that's why I give it this dotted line a lot of the time, to make sure we remember that it's not a physical thing. It doesn't have any sort of actual, you're not going to bump your head on a Gaussian surface. So something like that. And let's go ahead and label that while we're here. Now, in our top-down view, it doesn't actually matter what our shape looks like. So I'm kind of imagining that this thing is in what I said, the pill bottle shape, but it could be a square. It could even be something like this. And that's fine. Any of these are fine shapes to pick, as long as it's a prism, and as long as it's going essentially directly over to the other face, and they have the exact same area, A. I'm going to go with the circle because it's the easiest. But you kind of get where I'm coming from with this, I hope. Right? It doesn't matter what shape we take, and we'll see why. So, if I do Gauss's law to find this electric field, let's go ahead and write that out like we usually do. We need to think about the two separate pieces here that we're going to be dealing with. So first, what are the surfaces that the electric field is actually going to be going through? Well, I know the electric field looks, let's take a pale green color now. I like all these different colors. I know my electric field looks something like this, right? Coming perpendicularly directly off of this thing. Ignoring the fact that there's a little bit of a curve in my drawing here. But my electric field should be pointing like this, right? If my electric field is pointing like that, then these sides really don't matter. The only part that matters is the big faces on each end. That is to say, this side becomes 2 times E times A, where A is that surface area of my Gaussian shape. You know, at least the end caps. Now, the real question is, what is Q inside? We know that this shape has a charge density. That's a little bit pale, isn't it? Let's take a color that's a little bit darker then. We know it's got a charge density rho. So if we wanted to actually find, and I'll go ahead and label, here's my plus C naught, my minus C naught, probably should have included those. If we want to actually find what the charge is inside of my Gaussian shape, not all of it matters, right? All of this stuff up here, that's empty space. That doesn't have any charge in it. The only spot that I actually care about is this spot that I'm going to highlight in yellow. This piece right there, it's kind of a pale yellow. Let me bump that up a little bit. Make it nice and clear in the picture. That spot in yellow right there, the spot that I've highlighted in almost gold, that's the only spot that actually contributes charge. I'm going to say charge found here. If that's a little bit pale, that's okay. Don't worry about it, right? It's mostly for the narrative here. The charge is right there. So we need to find that. Q inside then is going to be my charge density times the volume that actually has charge. And what I've got here is essentially a tiny little cylinder. How do I find the volume of cylinder? It's the top the area of the circle on top times the height. So this is going to be the volume A to Z naught divided by E naught. Plug all of this stuff in. The 2 cancels out. And we're left with E is equal, and the A's will cancel out as well. Keep that in mind. That's the part where I say that the area really doesn't matter. When we do something like that, the 2's cancel out. I am left with rho Z naught over E. I want to make sure that I'm not doing anything crazy here. I think I might have slightly goofed up an earlier one. But that's the result that we get. And real quick, while we're here, let's go ahead and talk about the fact... Where did my... I hope I didn't just lose my entire palette that I had picked out for myself. I would scream. But I might have. That's okay. Let's go back to the default one real quick. That's really thick. We know from the outside here that the electric field of this thing normally, if we're going back to our slides here, we're expecting this to be eta over 2E naught. So does our answer that we just found agree with that? Well, the real answer is, how does rho relate to eta? If the same charge is to be found in each one of these, in eta, that would need to be multiplied by A to Z naught, whereas to find that same charge with a surface density would be just eta times A. The areas cancel out, and what we find is that eta is equal to rho to Z naught. We plug that in, we get back our same answer as before. Everything agrees, physics isn't broken, everything is fine. So, what happens now if we need to find this when we are inside of our shape? That's going to be a little bit more complicated. So what I'm going to do now is, let's go ahead and go over, let's redraw this thing out. Here's my shape, but now what I've got is a smaller piece like this, where now I'm only going up to Z and minus Z versus the full Z naught and minus Z naught. Right? Go ahead and fill these things in for the sake of it. Those are what I'm seeing here. So what's different? Well, the E times A didn't change. That should still be the same as what we just found. I'll go ahead and write this out, be explicit with it. E times A is still the same thing, right? We have 2 different faces where the flux is going through that surface area A. The Q inside is where it gets a little bit more funky. Because now we are no longer including, we don't have this empty space up top, right? We are only some portion of our golden box this time around, but luckily it's the same process. Q inside is still rho times A, but now it's times 2Z instead of Z naught. Right? We've got this little sliver of space and this little sliver of space that we're not counting anymore because they're not included in our Gaussian shape. So, everything goes just the exact same way. And what we find, which might not be surprising at this point, the A's are going to cancel out. E is equal to rho Z over E naught. Would you look at that? It is another linearly increasing electric field based on the distance away from the center. Getting kind of old at this point. We found the exact same thing for the sphere, the exact same thing for the line, right? We keep finding this kind of result here. but that's what we've got. For all of the Gaussian surfaces, the entire point is we make up some sort of shape that matches the symmetry of our object in some way or another. In a case like this, it's a planar symmetry. And that's why we often go with the circle, because this way, if I spin the entire thing, it matches the symmetry no matter what. But really, the area doesn't matter in a case like this. But it's supposed to match the symmetry in such a way so that EA is a very, very, very clean integral, right? We can just do that by multiplying most of the time. And without specifying what the area is, whether it is a circle or whether it's a square or whatever it might be, we can have it as a stepping stone here, and then it cancels out at the end. That won't always be the case, right? Because sometimes like R gets left over when we're doing point charges and everything. The infinite plane is just kind of a special case because there's no Z dependence, right? It's equal no matter where I'm at above the plane itself. So in this piece right here, did I write that down somewhere? I thought I had this. What I have is a cylinder of the slab. And it's not just, yeah. If I'm assuming that it's A, the volume of any cylinder or any prism in general, in fact, not just specific to cylinders. But if I have a top area A and some length L, then the volume of this entire shape is A times L. True for any prism. The 2 comes from the fact that I have E times A going through the top and E times A going through the bottom. We've also got that if it's a little bit, if it's a little bit more clear on this picture, the electric field is going through both ends of my shape. Fantastic question so far, though. Anything else before we keep moving on? All right. And quick reminder, I brought it up in the last lecture as well. It's not just you guys. If there is a question or anything else, if I'm like asking for questions, go ahead and type in question into the chat real quick. And that way I just know something's coming and I can, we don't have to spend as much time waiting for you guys to type. If I know something's coming, I know to wait. Otherwise we can just kind of jump right along. So let me erase these 2 points real quick because I'm going to get to those a little bit more organically. What happens when we don't have a symmetric shape? What happens when something's a little bit more funky? Well, Gauss's law will still work as long as the objects themselves have a symmetry that Gauss's law can use. So let's imagine this for a minute. I have a blue sphere with a charge density rho 1. And before I even say this, let's get rid of this piece for now. We could say Gauss's law looks like this thing, and let's imagine here for a minute that instead of being another spot, this would be, let me find my, let's imagine that this thing, oh, I didn't want to do that. Let's do this, was a hole in the middle of my blue sphere, right? Like a spherical bubble. How would I treat this thing? Well, I would want to find the electric field of both pieces and then add them up. But how might I do that for this hole? Well, what I can do is for a little bit, let me pretend as if it doesn't have a hole at all. Let me find the electric field assuming that it's completely solid. Then my electric field would depend on just the density rho 1. Now, if I wanted to add the electric field from the hole, that hole, I can equivalently say, instead of pretending as if there's a hole in E1, I could just say, hey, let me just imagine for a minute that it was solid, and then at this spot overlapping with my blue sphere is a second field. So I'm going to call this E of H, E of the hole, as it scales with negative ρ1. And so in that region alone, it cancels out the charge density that we might see in the rest of the shape. Now, if it was actually filled with another charge density, we can do the same thing. We just now add to it ρ2. Enough to cancel out what was there originally. To scoop out the hole, we subtract ρ1, and then we add in whatever other charge density we might need. So it's a little bit more complicated. It's not as clean because of the symmetry, like there can still be some symmetry to a lot of these problems, but as soon as you don't have concentric shapes like this, you lose the ability to just find wide ranges of the electric field. You're a little bit more limited in that sense, but it is still a method that you can use to find any of these values. So, here's another point that I know I've brought up a time or two, but I haven't talked about in any sort of real detail, and it's the difference between conductors and insulators. And you might already have a sense of what the difference between these two. Conductors generally allow charge to move through them. Insulators generally don't. But what we have been working with so far has actually been pretty much exclusively insulators. Conductors don't behave in quite the same way in a lot of senses. There's a kind of neat feature with these things, right? So conductors allow charges to move freely through them, right? They don't hold on to their covalent electrons very much at all. They allow them to just kind of move around in the sea of metal. So we have here something kind of similar. There is nothing holding any of these charges in place. They're acting like just a bunch of electrons contained in some sort of object. And right now, they're all kind of bouncing around, right? But let's give them a little while to see what happens. What we're expecting is that all of these charges are going to try to move to the outside of my shape. It turns out that that's how you get the most distance between every single localized charge, right? If I have all of these electrons or a bunch of positive charges, but generally it's electrons. If I have all of these electrons on a metallic object, the way that they can get as far away from each other as possible is by moving to the very outside. And maybe there's a couple floating around on the inside, but generally not that many. Most of them are going to be stuck to the outside. So all of the objects that we've been talking about, a sphere of charge or a cylinder with a uniform charge density, all of those things are not allowing the charge to move to the outside surface. All of those things have been insulators so far, right? And a consequence of a conductor moving all of the charges to the outside is that the electric field inside of a conductor is zero. And in fact, that doesn't just matter when it's naturally a metallic object. It's not just that it would naturally have an electric field is equal to zero on the inside. It's always going to have an electric field equal to zero on the inside. Let's go back to our simulation real quick. What do we find? With one bad exception here, almost all of these are confined to the outsides. And look what the difference is between the field on the outside and the field on the inside. I know it's not quite zero, but this isn't quite billions of electrons on a surface, right? For the most part, what we see, the electric field on the inside is almost zero, which again, this one's kind of, let me add a couple more. Let's shake things up a little bit. Let's see if they settle down into a little bit better of a rhythm here. But for the most part, what they're all trying to do, they're all trying to get to the outside. And when they're all trying to get to the outside like this, that's the most space you can possibly get between all of the charges, and it's going to be as happy as possible, right? This is all because of what we call the transfer of electrons. The ability to flow freely is all because of what we call band structure. This is kind of a visualization of what I'm talking about. If you remember electron orbitals from any of your chemistry courses, then you might remember that not all atoms have their electron orbitals filled, but atoms generally try to fill those when they can, right? That's what forms bonds. But if I had a metallic conductor, which most metals are conductors, and I apply some voltage, here's essentially all of my electrons in the orbitals. A little bit of voltage, a little bit of energy, kicks one up into an open lane, and it's allowed to start moving. I give it a little bit more of a boost, some more of them will get kicked up into some of these open lanes that we have. It's kind of like a traffic jam in a highway, right? Everything's jammed up in one spot, but if another lane opens up, suddenly a lot of these things can start moving along. It's just what happens. The voltage gets them instigated to start moving. Now, if I change that to an insulator, look at the difference here. The metal had, well, let's turn off the voltage for a minute. The metal had some open lanes up here, and there was all of this stuff in the low band, and the high band was pretty close by. We can't turn the voltage up enough to get anything up into the high band, but if we really needed to, if we really hit this thing with a lot of voltage, we could get some things kicked into the high band pretty easily. Plastics, on the other hand, are insulators. And insulators are generally going to have all of these bottom layers filled up. The amount of energy it would take to get one of these electrons into an open lane is going to be the space from this very top one all the way up to the bottom layer of the high band. And we can see that's quite a jump. And that's why all insulators will technically break down at a certain point, right? There's no way that you can permanently stop an electron from jumping to that higher energy state. You know, at a certain voltage, it'll just happen. But really, really good insulators will separate that out as much as possible. And then photoconductors are somewhere in the middle, but they're a little bit of a different kind of material. But that's really what's causing a lot of these things. And that's why like metal oxides don't have great conduction, because for the most part, they have now filled up those orbital shells and there's no more bands for the electrons to travel through. So let's go back to our earlier picture, and they're still mostly behaving with one or two that kind of float around in the middle. But again, we can kind of see that the electric field on the outside might be strong, but the electric field in the interior is at least trying to be zero. And then, of course, the best FET simulation, John Travoltage, has something kind of similar here, actually. If you rub your feet on carpet, you build up a bunch of negative charge, and we can see human bodies are not great conductors. They're pretty bad conductors, but they are technically conductors. And so that's why these charges are trying to group to the outside. Some of them are still on the inside, but they're taking a little bit of time to actually get there because it's not easy to move around through the human body. But we were talking about the breakdown voltage the other day, right? Same thing happens with static electricity. So, conductors are always going to try to maintain an electric field equal to zero inside of the conductor. So if I have my weird potato-shaped piece of metal, doesn't matter what I see on the outside, the inside is always going to try to be zero. If I punch a hole through this thing, and I put a positive charge in the middle, well, that positive charge is trying to create some sort of an electric field. Conductors don't like that. What they will do is they will move charge to the interior surface to cancel out that electric field. And we can see that in our simulation as well. Not John Travoltage, but back to this one. Let's kick in an external field pointing this way. And let's give it a minute, because they're all going to be dancing around for a little bit and trying to figure out what's going on. But we'll come back to that one. Generally speaking, anytime that we are in equilibrium, which means not thinking about circuits, and that's in a few chapters yet, the electric field inside of any conductor is always going to try to be zero. And on top of that, it's going to try and store any excess charge it has on the exterior surface. Anytime you see metal, we're generally talking about conductors. Anytime you're talking about charge distributions, where it's not just all grouped on the surface, we're generally talking about insulators. So, kind of a little bit of information to throw at you all at once, but let's try and use this immediately, actually. So a hollow metal sphere has an inner radius A and an outer radius B, right? And I say there's a net charge on this shell of plus 2Q. I put a point charge right in the middle of the gap inside of this hollow sphere. What is the electric field in these three regions? And then, how much charge is on each interior and exterior surface of my hollow sphere? Okay, so let's start to take a look at this one too. So, the first thing that we absolutely need to do is draw the picture. Make no mistake on this one, the picture will very much help. So I have a sphere. Let's do that in black. One sphere. Outer radius of the sphere. And we'll go ahead and make sure that we know it's a metal. And here is our point charge in the middle. Let's go ahead and label out some of these radii. So we've got to there, we've got to there, we've got A right here, B right here. Okay, so if we're clever with this, if we know what we're doing, and one more thing that I should write down on this is that the net charge on my positive shell is plus 2Q. If we're clever with this, we can rip through it really fast. If we know our concepts well, is what I should say. So the electric field, first we are looking for the area where R is less than A. Gauss's law, what does it depend on? We just skip to this part. What does it depend on? What is the charge inside? What's the charge inside? It's just our point charge, right? None of this outside stuff matters. So we can basically say, hey, this one's a freebie. This is just a point charge. And that's it. Now, what happens when we are looking in between? Well, it's inside a conductor. Done. That's it. Inside of a conductor, electric field is 0. Hands down, always. What about when R is greater than B, when we're looking on the outside? Now, I'm going to do the exact same thing as part A. So let's see it in action. I take this integral. How much charge do I have inside? Well, I've got the 1Q from my point charge. I've got the 2Q net charge from my shell. Total charge inside is 3Q. I'm outside of all of it at this point, right? My Gaussian surface is somewhere way on the outside. And what that means is that anytime I'm outside of a sphere of charge, it looks identical to a point charge. No different. Like that. And that's it. Those are my 3 electric fields. I'm gonna go ahead and erase. I don't have vector notation in there, so I should probably leave that as is. Because I have 1Q on the inside plus 2 more Q from the shell. My total charge inside is plus 3Q. Now, with all of that being said, part B is going to be a little bit different. We need to think about this in a few different ways. If I'm looking towards part B, I know that the electric field has to be 0 inside of here. I asked for this in black, please. Thank you. The electric field has to be 0 inside the conductor. So if I was to do Gauss's law, and let me, again, I want to make sure that we know that this is not a physical thing. This is just mostly there. And I'm going to do this real quick. It's a dotted line because it's a conceptual thing that we're using. That's my Gaussian surface. My charge inside, rather, let me start with the equation. Hello? Oh. My charge inside. If I go through all of these steps, if I take this piece, I know this is going to become E 4 pi r squared is equal to Qn over E naught. E is equal to 0. What does that mean? E naught's certainly not going to be 0. My Q inside must be 0. And that means that that's the sum of my positive point charge on the inside plus charge on the interior face. So charge int right here, right all along this outside. Charge int is equal to negative Q. Right? It has to cancel out whatever charge it sees on the inside. The interior face of that conductor is there to cancel out what it sees on the inside. That's it. It only does that. It makes sure that the E stays to be 0 inside of my conductor. Then once I get to the outside, though, we kind of already know what this thing looks like, but the other way to think about this is that the net charge on my conductor is plus 2Q. So if I know that there's a minus Q on the inside, there better be plus 3Q on the outside to make up the difference. All along the outside here, and my very, very sloppy value is plus 3Q versus the minus Q on the interior surface. And that's how we get our net plus 2Q. Now, this makes the electric field from a conductor very, very easy to find, because the only thing we need to know is the external electric field, or the external charge. The internal charge canceled out with whatever's on the inside, right? It might as well not be there. It might as well have all of the charge that I care about on the very outside of this thing. Because when I sum up all of the charges, I would have plus 3Q, minus Q, plus Q. Minus Q plus Q cancel out. I'm left with just 3Q on the outside. And that's it. These are almost more conceptual problems than they are actual solving problems. Be careful with those. You've got to have your concepts down. I have seen a lot of people get questions wrong on these ones. I had some questions like this on the exam last year, and I saw a lot more people than I wanted to get these things wrong because I don't think they understood the concepts well. I saw a lot of people trying to tell me that the electric field was anything other than 0 inside of a conductor, and it's always going to be 0. And that'll help you figure out a lot of things. So, it will often say if it's a conductor or not. So the question is, how do we know whether it's a conductor or not? If we say it's a metal or if we say it's a conductor, right? It will either explicitly say it's a conductor or we'll say it's metallic. And if it's metallic, I don't know of any I'm sure there are some. I shouldn't say that. But most metals are conductors. Even if they're not all equally good conductors, they're all conductors, I think. So if they say it's made out of metal, then it's going to be a conductor. Otherwise, yeah. If you ever see something that has a uniform charge density, or if it's plastic or something like that, it's an insulator. If you want to know whether something is a conductor or an insulator, a good rule of thumb is, would you touch it if it was on top of a stove? A wooden spoon? Sure, that's an insulator. A metal pot? No, that's a conductor. It just so happens that good electric conductors are often good thermal conductors as well. Not all. There are exceptions, but general rule of thumb. So let's keep digging in, because I got another one for you now. Here, I have two conducting spheres. So one's a spherical shell with an inner and outer radius, right? So it's not infinitely thin. It does have thickness to it. And the other is just a sphere, not hollow. I don't know anything about the charges on either of these, but I do know where the electric field, or what the electric field looks like in all cases. So before we jump into this problem all the way, though, let's get an idea of what kind of values we're expecting to find for some of these. What we see on the inside here, between these two spheres is an electric field pointing inwards. What kind of charge are we expecting our inner sphere to have? We're expecting a negative charge. Right, we're expecting a negative charge here because there's an electric field pointing inwards. Now, that doesn't say anything about the electric field on the inside of that sphere, which inside of a conductor, we know what the electric field should look like. But ignoring that, now look towards the outside. The outside is pointing radially away. What does the net charge of everything summed up together have to be then? The net charge of everything better be positive. So, doing something like that just helps make sure you're kind of on the right track for finding a lot of these values, right? If we see anything other than what we're expecting to see, that's some red flags that we need to start asking ourselves some questions. So, one of the tricks that I use for when I'm solving problems like this. But anyways, go ahead, get started working on this one. Find those three charges. All right, it's a fine time to start looking at this one. So, what I'm going to do here is I'm going to label these things. Let's try and make this a little bit easier. So let's go ahead and label these in orange. Sure, orange. I'm going to call the inside, that's surface A, and then I've got surface B, and I'll have surface C on the outside, just to help keep track of everything. So, we start with Gauss's law, somewhere between the two. So something like, that's not a very good sphere. Let's make it a little bit more sphere-like, something around like, right like that, right? A circle, something like that. Okay, what is my charge inside? Surface B, surface C certainly don't count. There's no charge interior to my conducting sphere because it's a conducting sphere, so all the charge is on the outside on surface A. But let's talk about what that means for the electric field. So in a case like that, we are looking at an electric field. We have that. Call it E of A, right? That sounds fair. Let's do our Gauss's law. Might as well go through this thing. Q inside divided by E naught. Q inside, the only part that's inside is QA, right? The surface on surface A. Charge on surface A. There we go. Got to twist the words around a few times until it makes sense. Okay, so just like always, call it Q of A over E naught. Rearrange it. Whoops, I don't care about E of A. Care about Q of A. And this should be this piece right here, which is going to be negative 10.68 nanocoulombs. Because again, it's pointing radially inwards. Radially inwards is what I'm expecting to see. Now, I could have jumped through a few of these steps. I went through Gauss's law this entire time, but one of the things that I could remember is that anytime I'm outside of a sphere of charge, it looks just like a point charge. So I could have instead immediately jumped to say, hey, isn't it true that E of A would be equal to Q of A over R squared? And we could have just gone right from there instead of writing out the things from Gauss's law, but you don't save too many steps. It's not a big deal, right? Whatever makes sense. So let's go ahead and box that in real quick, just for fun. There's answer A. Now we move on to part B, right? What is the charge on surface B? As we're looking at this thing, I am now looking at a point, and let me see if I can draw this thing properly. Oh, it stopped drawing on me. Come back to me. What about now? We're looking at this kind of Gaussian surface now, right? Where we know the electric field must be 0. What does that mean? That the charge inside of my Gaussian surface must sum up to be 0. I just found negative 10.68 inside. I must also find positive 10.68 inside. Q of B must be the negative of Q of A. Does that step make sense? Now, as we're going with this, we're looking at our last bit. We are drawing our Gaussian surface way outside like this, right? Also, keep in mind one other thing I should specify. Let me go back a step. When we were plugging in R, remember that R is equal to 8 centimeters in this case. Anytime I'm dealing with my sphere acts like a point charge. Treat it as if it's a point charge, and that means my radius from the center. That's the key part. So it's 8 centimeters, not 3 centimeters. So as we're looking for QC, I'm going to do Gauss's law. I'm going to sum up all of the charges on the inside. So Qn, so let's say exterior surface. Let's specify real quick. All of my charges on the outside. Qn is going to be Q of A plus Q of B plus Q of C. Q of B is the negative of Q of A. These two cancel out. Q of N, well, Qn is equal to Q of C. I already know what my electric field looks like. I already know I've got a big sphere. Plug in a radius of 17 centimeters, and we should find for QC, remember, a positive value. We're expecting a positive charge to give us a radially away electric field. And when we plug in all of those values, we should find something like 48.21, and I'll specify positive 48.21 nanocoulombs. The inside does have an effect. Like what we saw going on, and there goes my draw pad again. It like stops working 5 seconds after I start using it. Where were we on this one? It was this one. If the point charge wasn't in the middle here, the conductor would have had a net charge of plus 2q. The inner surface would be 0. The outer surface would be plus 2q. The interior of the conductor always changes its charge to compensate for what's inside of it, to cancel that out. So when you're solving things, you can neglect anything inside of the conductor. But it is still having an effect. There's a physical effect on the conductor because of it. But you only have to consider the outer charge when you are solving it. Let's go ahead and look at our last one. So this doesn't have a conductor or anything else like that, right? This is actually more in line with what we were looking at last time, but it's still pretty important. Let's imagine that we have a solid sphere of radius capital R and charge positive, capital Q, these two things, but it's got a non-uniform charge density. Rho is equal to C over R squared, where C is some constant. Non-uniform charge density, but a charge density means this is not a conductor. This is an insulator. First, I want you to see if you can find what is that constant C in terms of R and Q. What is that constant C and other things as needed? And then, if you're feeling good about that one, what is the electric field inside of this sphere? So what I'm going to do here is I'm going to give you a little bit of time to work on this one by yourself first and just focus on seeing if you can get through part A. If you can get through part A, part B actually looks really, really similar to it. But let's go ahead and focus in on part A. You've got that extra term for your integration for dealing with that thing. And I'll talk about that one a little bit as I'm working through this problem. But I'll go through part A and then give you a little bit more time to work on part B. And that way, even if part A is really confusing, you've got a fighting chance of part B. Okay, I think I want to start to look at part A, just so we've got a little bit of time, and we can spend some time after that working on part B here. So I'm going to draw this thing out, but it's not going to be anything really special. I've got a sphere. A sphere that I can't draw. A sphere let's try to draw now. There we go, something like this, and it's in the wrong color. Something like this. There we are. And let's go ahead and I want to fill this thing in with a color here. So let's do this color. Nice weird fuchsia. Called quicksand, I guess, but that's fine. So I really don't care what's happening on the outside, right? As long as I'm doing this thing, the only thing I really care about what's going on the inside. And so my Gaussian surface might look something, Gaussian surface, dotted line to show it's not physical. Just so we're all on the same page, I just want to be absolutely clear on everything that I'm talking about here. Doesn't hurt to go a little bit overboard just to make sure we're all on the same page. So little r, big R, Gaussian surface. I know that this thing has a total charge Q, but a charge density C over R squared. And I am using little r here because it's a little bit strange. At different r's throughout this thing, it's got a different charge density. Right? That's what we're trying to say. It gets smaller as we go out and out and out and out and out. So, how would we go about finding this value C? Well, we know that Q comes from total charge, which if this was a uniform density, I could just say rho times V and call it a day. However, because we are dealing with a non-constant uniform or a non-constant charge density, what we really need to do is take an integral. Right? That's what we're really trying to get at here. Anytime you've got these constantly changing bits, integration gets involved. So I'm going to be taking an integral of rho dv, where rho is a changing variable. So let's plug these things in. And we were given a hint as to what dv looks like. We were told that we can use a dv is equal to 4 pi r squared dr. And I want to talk about where we're getting this thing, because I imagine you probably haven't seen a lot of these types of integrals before. But what we're basically saying is, how do you create a volume in an integral like this? Well, what I'm doing is I'm essentially taking a tiny little bit and I'm covering it in a layer of paint. And then I let it dry and I cover it in another layer of paint, and then another layer of paint, and then another layer of paint. And every single time, that paint is super thin. How thin? dr. And it's covering a surface 4 pi r squared. But every single time I add that next little tiny layer, it gets just a little bit thicker, and I keep doing that until I'm my full size. So if we plug in these values, what do we find? It's c over r squared times 4 pi r squared dr. And we're starting from 0, and we're going all the way out until we reach the edge of our shape, until we have made the full size. So that's capital R as our upper bound. Now this integral is actually a lot easier because my r squareds are going to cancel out. So this is just going to become c 4 pi capital R minus 0. C is equal to Q divided by 4 pi R. Now, I'm not going to use that immediately. It's a lot easier to do part B without plugging in C immediately. Wait until towards the very end to plug in C. Your life will be a little bit easier. But this is a very similar process to what we need to do to solve out part B. Because the integral is not actually E dot dA. That's the part we can solve like we always have been. Qn is actually the tricky part of that problem. So go ahead and work on that one for a little bit longer. And then we'll come back and look at part B as well. I'm going to say 5 minutes or so. So 354, 355, and then I'll blast through that at the very end, and we'll call it a day. Okay, let's go ahead and close this one out. So, as I was saying, there's not really a huge difference between part A and part B here. We do have to be a little bit careful with our notation, but it's really going through a lot of the same method. So for part B here, we are trying to find the electric field at this radius lowercase r. And as I've been saying before, we're still dealing with a sphere. That hasn't changed. And so if we're actually looking at the full side of this thing, E dot dA is equal to Qn over E naught. This really hasn't changed. This is still just E 4 pi r squared. Right? It's still a sphere. Nothing has really changed in that regard. Qn is the tricky bit. So what we'll have to do then, let's go over to the side here. And let's say, all right, we're dealing with Q inside, and we're going to take a very similar method to last time. But now, the difference is we are no longer going all the way up to capital R. We're going to go to a new value. And I'm going to call this, value R1. And the reason I'm doing that is it's not anything special. I'm still trying to find the field at a radius R. But can you see how it might be a little bit confusing that we've got R inside as our integrating term? We're integrating over R, but then we would plug in R again, and that's confusing, I think. If you're not used to doing that, if you haven't done it before, it's a little bit sloppy to do it like that anyways. What is sometimes used instead is sometimes we'll call this term R prime and R prime squared and R prime squared. But if you've been doing anything with differential equations recently, you might recognize that as the same symbol that we use for derivatives sometimes. So that's confusing. So that's why I'm using R1. It's arbitrary. I'm just calling this something different so we can specify, hey, this is what I'm plugging in, and R is the value that I'm integrating over while I'm here. But the integral actually comes out to be the exact same thing. So this is going to be C 4 pi R1, right? With that one exception right there. Once we have that, I'm going to bring that thing back over and I'm going to say, hey, Qn is equal to this thing, but remember what I said. R1 was a placeholder. Make it R again. No big deal. Right? C 4 pi R over E naught. And I just want to do that because, again, we can plug in any value for R here. R1 is just one specific value. We plug it in, and then we're done with it. So we come over here. We say, okay, the 4 pi, that's actually going to cancel out from each of these, and that's fine. R squared, move it to the other side. So I'm going to see something like C over R E naught. Now at the very end, I can go ahead and plug in for my value for C. And that's what we find. Or something like that. There we are. Well, with that, we will close out our 24-3 lecture.